Hello everyone, welcome to the second session of linear programming. Today we are going to solve a linear program, a problem, a minimization problem graphically. So let's first go on to the first slide, that is let us first discuss the problem. Here comes the problem. Uh, it is about diet. So Munal has two food items at his disposal. And he has to choose the right combination of the two food items and the daily dietary requirements. So here we are considering only three nutrients. One is calcium, protein, second one is protein and vitamin A. Now the problem here is to choose the correct combination of the two food items, which actually has to be chosen keeping in mind the minimum cost. And of course, the minimum dietary requirement has to be met. So this is the problem. So let's first formulate it in terms of a linear programming problem. So we have this dietary requirement, and given this, um, we can see that this the problem here we can see that the food one has a cost of $0.6 and food two has a cost of $1. So let amount of food one purchased by Munal be X1. Right, let me choose a food color. Yeah. So let X1 be the amount of food one purchased and X2 be the amount of food two purchased. So in this case, then uh, the cost will be C. Let the cost be C is equal to 0.6 X1 plus X2. So we have already discussed how to formulate in the previous sessions. So I'm just writing the constraints. So subject to the constraints, the constraints are first one. So the calcium constraint. The calcium constraint is 10x1 plus um, from food 2, the 4 bits of calcium can be obtained. So 4x2. And that has to be greater than equal to 20 because 20 is the minimum requirement, right? Um, Similarly, we can go in for the next, the other constraint, and let us write down constraints. So I'll just erase this part and write the second constraint. Now, the second constraint is 5x1 plus 5x2 is greater than equal to 20. And let me write the third constant. I'm writing it over here. 2x1 plus 6x2 is greater than equal to. Alright, so and of course finally we have the non-negativity constant, that is x1 and x2 are greater than equal to 0. Alright, let's see have a final view at the problem. So the screen gives us a final view at the problem. Now when we start with our the graphical solution. First, we convert these constraints. We view this as equations. So we write this in equation form. So to write this in equation form, we'll have the first one is 10x1 plus 4x2 is equal to 20. And then we have 5x1 plus 5x2 is equal to 20 again. And the third equation is 2x1 plus 6x2 is equal to 12. And of course, the non-negativity constraints. Mm, Let us now start with our plotting. To plot, first we choose the calcium constant. Because 10x1 plus 4x2 is equal to 20. And what we do here is we first set one of them. We set x2 is equal to 0. When we set x2 is equal to 0, then our equation becomes 10x1 is equal to 20. And so x1 is equal to 2. Right? So you can see here that x2 is 0, x2 is 0. When x2 is 0, x1 is equal to 2. Now let's do the same thing where x1 is 0. So let's set x1 equal to 0. When x1 is equal to 0, then we have 4x2 is equal to 20, right? So x2 will be equal to 5, that is 20 by 4, that is equal to 5. So here again, you can see that when x1 is equal to 0, x2 is equal to 5. So we have 2 points of this straight line. That is 0, 5 is 1 point, another point is 2, 0. So let's now plot these 2 points and get the straight line. Because this is linear programming, so all the constraints are linear. Of course, the objective function is also linear. So that's why this is linear programming. So if it hadn't been linear, it would have been non-linear. But for now, we are discussing linear programming. Next, we can see that we have plotted here, as you can see, this is the point 0, 5, all right, and this is the point 2, 0. So we've drawn a straight line between these 2 points and we have got our calcium constant. So this is the calcium constant, right? This line gives me the calcium constant. Again, now let's go to the protein constant. So this is the protein constant. In the same way, we set x1 equal to 0. X1 is equal to 0. So when we set x1 equal to 0, we have 5x2 is equal to 20. So x2 is equal to 4, as you can see in the table. And same way, when we set x2 equal to 0, we have 5x1 is equal to 20. And so we have x1 is equal to 4. So we get 2 points, 0, 4 and 4, 0. Let's now plot this again, right? So we have plotted this. You can see this is 0, 4. This is 0, 4. And this is 4, 0. So this is our protein constant, right? Next, let's go to vitamin A constant. And in the same way, it was, maybe it's a bit boring because we're doing the same thing over and over again, but nevertheless, it's better to explain. Um, okay. Now, again, we set x1 as 0, x1 equal to 0. And so we have 6x2 is equal to 12. And so we get x2 is equal to 12 by 6. That is, so you will have here 0 and 2. This is 1. Then we said x2 equal to 0. And so we have, when x2 is equal to 0, we have 2x1 is equal to 12. And so we have x1 is equal to 12 by 2, that is equal to 6, and we get this difference, right? So we have 2.02 and 60. So we get here the vitamin A constraint. So this is 0, 2, and this is 60, and this is the vitamin A constraint, right? Okay. Let's now see which is the feasible region. So this area, as it is marked over here, this entire area, this is the feasible region. Now, why this is the feasible region? Because all the constraints are greater than equal to constraint. So we can move to the right hand side and not to the left hand side, because when we are moving left hand side, the nutrients are less than the daily requirement. So it can be more than the daily requirement, but not less. So that's why this is the feasible region. Let me take a different color and mark it. So this is one of the extreme points here. This is too light. Yeah. So this is one extreme point. Okay, and it is upwards, moving upwards, because we have taken this part because we know that both the variables x2 and x1 are non-negative. So this is one extreme point. This is another extreme point. So extreme points are the intersection of two constraints. This is one, and this is one. So we can say if we mark it, this is A, mark it as this extreme point as B, this one as C, and this one as D. So we get A, B, C, D. So these are the boundary of the feasible region. So to the right side of these points, this boundary, we have our feasible region. So the solution set has to be any point on this feasible region or on this boundary, right? So let's now, to find the feasible region, of course, this is a minimization problem and we have to go to our objective function. So let's now go to the objective function. So this is the objective function. So C is equal to 0.6x1 plus x2. Now we take an arbitrary value of C. So here we have this objective function. We take an arbitrary value. Here I have taken 6, a small tip. Why have I taken 6? Because it is divisible by 0.6. And of course, this is 1, so it won't matter. So I usually try to take this arbitrary value, which is um, a kind of multiple of these two coefficients, so that it is divisible by both the coefficients. So I've taken it as 6. So now, because in that case, I'll get whole numbers and it will be um, convenient for me to draw the straight line from the points. So let me take again, I'll put the same, I use the same method. So I put x1 equal to 0. So when I put x1 equal to 0, I get x2 equal to 6. Right? So I get the first point, 0, 6. So this is for the objective function. Then for the second point, I'll set x2 equal to 0. So when I set x2 is equal to 0, I have 0.6 x1 is equal to 6. So I have x1 is equal to 10. So I have the next point 10, 0. So let me now plot this in our diagram. So now we have our objective function, this yellow line. And so this is, you can see 0, 6, and this is 10, 0. All right, which we are doing. So this is visible. That means it is satisfying all the three constraints. That means all the nutrients are met if the solution is on any point on this line over here because it is in the visible region. But our objective is to minimize the cost. This is the cost function. So we have to slide this towards downwards so that the cost is lowered, but it is not outside this visible region. It cannot come down to this side. It has to be within this visible region, but as small as possible. So cost will be lowest, but visible. Okay, so we simply slide this downward. Let's slide it down. So we have slid it downwards. So it is still in the feasible region, but we can see from here that we can still go down. Cost can be further minimized. So we have brought it down again. So you can see that it is intersecting to one of the extreme points, but still there is scope of reducing the cost. It is in the feasible region, there is scope. So let us slide it further down. So it cannot be slid further down because if it is slid down, it will be outside the visible region. So this is the minimum possible. This is the point where the minimum possible cost is attainable. And from this here, you can see that if I read this here, you can see that this is here x1 is equal to 3 and x2 is equal to 1. So we have got a solution that is x1 is equal to 3 and x2 is equal to 1. We did it because this horizontal axis it is measuring x1 and the vertical axis is measuring x2. So we have x2 is equal to 1 and x1 is equal to 3. So here we have taken it down. X1 is equal to 3, x2 is equal to 1. And so we find the cost. So we put it in our cost function. So 0.6 into 3 plus 1, we get to 0.8. And let's see if the constraints are satisfying. It will satisfy the constraint. So 10x1 into this is 3. So we have 10 into 3, that is 30, and plus 4, this is 34, so of course greater than 20. Next one, that is 5. 5 into 3 is 15. X1 is 15. Plus 5, that is equal to 20. So this is equal to 34. It is satisfying the calcium constraint. So it is more than satisfying the calcium constraint. This is exactly satisfying the protein constraint. And in this case, 2 3s are 6 plus 6 into 1, 6 is equal to 12, exactly satisfying the vitamin A constraint. Right? So we have solved our problem, minimization problem graphically. Okay, so that's all for today. So if you are taking a graph paper, so you can solve it in this way. You can draw the objective function and then you'll directly get the answer from this graph. So this is just for demonstration. So in the next session, we'll be solving graphically a maximization problem. For now, thank you and